isomers. So isomers, these are molecules that have the same molecular structure, but then they look differently based on their connectivity or how they are in their rotations. So the first isomer I'm going to go over is structural isomers. So these are the least similar of all isomers. They only share the same molecular formula and weight. So they have the same chemical composition. So they have all the same chemical makeup, but then they have different chemical properties and also physical properties. So when writing them, their formula, they'll look the same, they'll have the same molecular weight, but when drawing them out or writing their IUPAC name, they'll have major differences. So as you can see on this right side, these three molecules, they all have the same chemical formula and molecular weight because they're made up of the same elements and the same amount of each element. But because of their connectivity, they all look pretty different, and that leads to them having different chemical properties as well. So these are structural isomers. They're the least similar of all isomers. Next, I'm going to go into stereoisomers. So these are more similar than the structural isomers. They do have the same chemical formula, but they also have the same atomic connectivity. So these will have the same bonds, but they just differ in how the atoms connected to each other are arranged in space. So when I go over their connectivities, usually they draw the molecules using wedge or dashed lines or solid lines. So within a solid line, we assume that it's like flat against the page, but for wedge lines, we usually assume they're coming out of the page, and dashed lines that they're going into the page. So stereoisomers, these include all the isomers that are not structural isomers. So stereoisomers, they include conformational isomers and configurational isomers. So these isomers, they're still different, but they're more similar than the structural isomers that just share the same chemical formula and molecular weight. These have the same connectivity. They just differ in how they're connected the same, but it just differs in how the bonds look when they're connected. So the first stereoisomer is conformational isomers, sometimes also known as conformers. So these are the most similar of all isomers. They're basically the same molecule, but they're at different points in their natural rotation around a single bond. So single bonds, they're unlike double or triple bonds, that they can move about. They're not as rigid as single and double bonds, so the molecules can rotate while connected to each other in single bonds. So like I said before, they vary in the degrees of rotation around a single bond, and this creates different levels of strain. For conformational isomers, they usually use what is known as a Newman projection. So that is the two molecules on top. So the ones with the circle and the lines, those are known as Newman projections, and they're usually used for conformational isomers. This is because this allows the molecule to be visualized along a line extending through the carbon-carbon bond axis. So the circle represents the bond between the two carbons, and then where the three lines meet up, that's the carbon. So on you can see there's where the three lines meet up, that's on a carbon, and then on the other side of this circle, you can assume it's the other carbon that's attached to the carbon that you can see here. So the Newman projection, it looks directly across the bond from carbon to carbon. And this is done to show how the three substituents connected to the carbon bond, how they stack up to each other and how they look as the bond rotates. So on the top left molecule, you can see that the carbon-carbon bond, the substituents are on top of each other. So this creates more strain on the bond than if it was at the rotation on the right side, where all the substituents, they're separated from each other equally. This would be more favorable because the substituents aren't directly on top of each other, creating strain on the single bond. And then on the bottom, it's a more detailed representation of how the bond looks between the two carbons. So instead of looking directly across the bond, this gives like a bird's eye view of the bond between the two carbons. So these are conformational isomers. So the left and the right, they're both the same molecule, but they just differ in how the bond rotates. So at which point of the bond rotation these two molecules are in. So that's conformational isomers. They have different conformations that they can be in. So the first is a staggered conformation. So this is when the substituents aren't directly on top of each other. They're separated from each other equidistant. So like I said, there's no overlap of the atoms along the line of sight in a Newman projection. They're each substituent is in between the two substituents on the other side of the bond. The first type of staggered is anti-staggered. So this is when the two largest substituents are anti-periplanar. So this is when they're on the same plane but on opposite sides. So as you can see on the bottom, the two big methyl groups are on the same plane, since they're both a solid line, but they're anti because they're directly across from each other. They're on opposite sides. This is pretty favorable because they're not in each other's space. There's not a lot of strain on the single bond. They're given as much space as possible because the hydrogen bonds are a lot smaller than the methyl groups. So because the two methyl groups are directly across from each other on opposite sides, this is pretty favorable. There's not a lot of strain on it. Gauche is the next conformation. It's also staggered, but it's not as energetically favorable as anti, because there's only a 60-degree difference between the two largest groups. So I can see on the top, this gauche formation, the carbon groups are still not on top of each other, but they are pretty close to each other. They have a 60-degree difference between them instead of the 180-degree difference between the methyl groups and the anti-conformation. So those are the two different staggered conformations. When the substituents are on top of each other in the Newman projection, this is called the eclipse conformation. So for just eclipse conformation, this is when the two methyl groups, or the two largest substituents, they're 120 degrees apart, but they still overlap. So there's an overlap of the hydrogens on the adjacent carbons. So as you can see on the bottom figure, the substituents are on top of each other, but the methyl groups are still 120 degrees away from each other. This is more favorable than what is called totally eclipsed. So this is when the methyl groups are directly on top of each other. There's 0-degree separation between them. And this has the highest energy state because of the strain caused by the two methyl groups being right on top of each other, but it's energetically unfavorable because of how much strain there is on the molecule. It's not favorable because of that. So when the two methyl groups are on the same plane on top of each other, this is what is known as syn-periplanar instead of anti-periplanar. So they're on the same plane on the same side, and this causes the total eclipse conformation. So for these conformational isomers, they can interchange between each other because of the small amount of energy needed to rotate a single bond. So just a small amount of energy is needed to convert from the staggered and the eclipse conformations. So a molecule can interchange between them. And this is why they're pretty similar, because they're the same molecule, but just because of the bond rotation causes these conformational isomers.